So good evening. My name is John Watson, and this is a weekly live meeting for SNHU's Computer Science 260, Data Structures and Algorithms. We're looking at week 3 this week, and we're going to go over the linked list problem. So like all of the problems, the first thing we want to do is download the zip file. We'll go ahead and extract it. And then, as before, you've got your instructions in here and you've got some sample code to start with. Now, if we look at the instructions, you'll notice compared to previous weeks, our menu is growing. We've added an option to load bids, display bids, find bid. And the thing with the linked list this week is, or in the whole list, are what we call abstract data types, which, let's see here, I've got a picture of it in the textbook. Abstract data types are types that you construct that you use to hold other data. One of the things about ADTs or abstract data types compared to, say, built-in frameworks is there's a concept of kind of a signature or an interface, or the idea or the notion is that if you're going to code something, you want to support the kinds of operations or methods that are expected. And that's why in our instructions, we state that we're going to have an append method, a prepend method, print list, remove, and search. And so the goal in this class, or this exercise, is to be able to take the starter code and be able to build a linked list to store our bids. So I'm going to start doing that right now. As before, we go into an Eclipse and we start a new project. C++ project. We choose Hello World and our compiler for the platform we have, and the project is Lab 3-3. And once it's been built, it automatically creates a file called Lab 3.3, but you could rename this if you wanted to, or leave it as is. And remember from our instructions, one of the first things we want to do is to make sure we go and add the compiler option, because we're going to be using some of the newer C++ constructs. So to do that, we right-click on the project in the Project Explorer, choose Properties, C++ Build, Settings, go to our compiler and the miscellaneous, and we can just go ahead and paste this entry here. And now we have set our default standard to C++ 11 or 2011. And then if I look at my workspace folder, I now have Lab 3.3, which is a project I just created. I've got a source folder and just the Lab 3.3. So what I'm going to do here is select all the files that we want to use, and I'll drag them over here and let them go. So now they're in the source folder, and then the simplest thing in Eclipse is to simply right-click on your project again and choose Refresh, and it's going to reread stuff. I actually don't need the Lab 3.3 because we started with a program called Linked List. So we'll just go ahead and delete this guy, and here's our starter code. Now, one of the first things we want to do is take a quick review of the starter code. Let's see if I could find, is that the outline? Yeah. If you're not familiar with this, what you could also do, oops, you can choose this button over here for outline. If you had done that, and it opens up a window, let's see, it lets you see the outline of the code. That's right. What I actually want to do is click this is to restore the window. That'll stick it on the side. You can hide it, and you can just pop out a little option if you want a quick peek, or you could stick it by choosing this restore button. So I'm going to actually make this go away and restore it so we can refer to it. This outline is a helpful feature. Instead of scrolling around and looking for stuff and trying to scan, you can use the outline to select parts of the program. So there's, for example, an append method. And notice we have our now famous fix me's. And there's a prepend and so on and so forth. So we've got all of these boilerplate code, and there's as usual, there's a main method. There's one slight addition to the main method. and that is for the command line startup, we have an optional second argument. So the first argument is always the path to the file, and the second argument is an optional bid key that you want to search for. And again, we're trying to just keep it fairly simple. If you don't pass anything, then it's going to default to the December file, assuming it's in the current directory, and it's going to start with a bid key of 98109. So if when you're writing your code, it always displayed the same value, it's because you didn't pick up on this. And we'll show this and kind of prove it when we get some working code later. And here's our menu options: enter, load, display, find. The enter bid we just left, that's from before. That's not really interesting. The load one is the interesting one. So we're going to have to implement a load bids method. And we've got a print and a search. Looking back at the code again, here's the steps we're going to follow. But I also want to point out too, if you hadn't seen this or looked at it before, we showed you some example input and output from running the various choices. So for example, when you choose choice number 2, it tells you load in CSV file, the name of the file it's loading, and how long it took. And the same goes for choice 3 when you display them, choice 4 and choice 5. So let's go back up. Take a little side trip for a minute. We'll go back and review zyBooks, and we're going to look at the linked list. And we're actually implementing a singly linked list, which is simply a list that goes one way or has pointers for one way. And you can kind of see what it looks like visually here. Here they've got a structure called numList. It's a list of numbers, and it has a head pointer which points to the start of the list, and that gets you the first node entry, which in this case is a value 66, and there's a next pointer that goes to the next item. And so this way of linking or chaining this list of items or nodes together is the concept we're going to implement. So let's look back at the code and see what we've got here. Where's my little fix me thing? Oops, I do this all the time. Restore that to the bottom, switch to tasks, and our first fix me is we need to construct a node. So let's back up just a second. We've given you the bid structure that we want you to store. So if we look at what a node looks like, we know that it's got to have a pointer. And we also know it's supposed to store some piece of data. In this case, the data is an integer. So in our case, we're going to come here and we're going to create a struct called, oh, I don't know, how about node? Seems like a useful term. And then the data value we're going to store is one of these bids here. So we're going to, data type would be bid, which is the structure. Lowercase bid is the actual member name. And then we're going to need, this is a node pointer. Next. Now, you can actually put the asterisk for the pointer on the element or next to here. So I could do it this way if I wanted. I could even do it this way if I wanted. I find that this, I don't like this with spacing because it starts to make my brain think it's a multiplication when it's not. A lot of people, and perhaps even the book, likes to put it next to the variable name to let you know that it's a pointer. When I learned this stuff years and years and years ago, we used to do it this way. So this was a way of saying next is a variable name, and it's not just a node, but it's a node pointer. So that's how I think of it and refer to it, and I personally tend to do it that way. There is no right or wrong. It's going to be whatever you are comfortable with, or more importantly, when you're working with a team or in a shop somewhere, an organization, that there's going to be standards and hopefully everybody follows so the code looks somewhat familiar and similar, and there's not widely different styles. Now, I don't remember if this was here last week, but so this structure called bid, there's a constructor, which is a method that's automatically called when you create a new instance of something, a class or a struct. In this case, the constructor, or what we call the default constructor, is simply the name of the item, bid or class or struct, with parentheses, empty parentheses. So every time we create a bid, what's going to happen is this code in the default constructor is going to be called. So what we did in here was we put an instruction to say we're going to make sure that the amount is set to 0. We can use that same concept here because it's an important thing that we need to do. Remember that the key concept of a node is this next pointer. And basically, it's going to point to some memory address. It's going to have some long string of numbers, which is the actual memory address. But we won't really know if there's a next node or not unless we follow a kind of a convention or standard. And the convention is we want to constructor. It's the name of the class or struct, followed by this. And we're going to say next, which is our variable node pointer, equals. You can use the old-fashioned C standard of null. Oh, notice this actually reports an error, or the newer construct of null pointer. That's a special. Notice once I typed it, it came in and changed color. So what happens is every time we create a node instance, the default constructor will be called. It will automatically initialize the next pointer to be null. And this way there, we can later test if that's null. That's how we know we've gotten to the end if we're, say, looping through all the items in the list. This is a kind of an important safety feature we want to put in so that anytime, you could even set bid if you wanted to do stuff or whatever, but this is kind of an important thing we want to make sure we do. Let's take a moment. So we define what the structure is. And remember to initialize housekeeping variables in the constructor. Let's see. When we construct a new list, we look at our linked list. Let's see what we have for housekeeping. We don't actually have any housekeeping. So not only do we need this definition of a node, but we're going to need another node pointer here, which we'll call head. And this is part of the linked list class. If I collapse this down, that's just a structure definition for node. The linked list contains the head pointer, which is this guy here that tells you where the start or the head of the list is. We want to make sure we do the same thing. We want to initialize the list to null. So we'd say head equals null pointer. That way there, when we create a new instance of linked list, we are sure that it's not pointing to anything and we know that the list is empty. The next thing is to implement the append logic. And let's take a look at what the program logic is doing. So if we go down to the main at the bottom, we've got load bids. We give it a CSV path and we give it the address of the bid list that we want loaded, which notice we said the bid list is a linked list, this class. So we've got an instance of our linked list that we're building up above, and we're calling it bid list. And we're going to pass that to the load bids routine. So if we go and just take a quick peek at the load bids routine, if I could find it. There it is. There's our path, there's our list pointer. We're going to output loading the file name. We're going to use the parser just like we did last week. And we've got a good old loop. So we're going to loop on this and create instances of a bid. And then you can see here we're calling the list append method, giving it the bid we just initialized from the file. So every time we read a row from the file, remember our standard bid file looks like so. Every time we read a row, we're going to create a bid instance with this data, and then we're going to call the append method to append it to our linked list. So now look at the append method, and you can see we're receiving a bid, and we've got not much else there. So the first thing we're going to do is we're going to create a node. because remember, the linked list doesn't store bids, it stores nodes. So we construct a node pointer, node equals new node. And this is worth a little bit of an explanation. When you create a variable such as, let's find it, this bid here, this is created in an area that we call the stack. It's basically local memory. It's super fast. It's super easy to access. But when you're working with large data sets, you want to use something called the heap. The heap is, a stack has a small fixed amount of memory. The heap is kind of like all the other memory that's left in the computer or that's available to the program. So if you've got a 32-bit machine with 4 gigs of memory, and let's say we give off a gig for device drivers and the operating system and everything else, then maybe you got 3 gigabytes left. So a program might take up, I don't know, let's say half a meg. So, which is really nothing compared to 3 gigabytes. So the heap would represent up to 3 gigabytes of memory that you could use and access in your program that would be available to it. And so in order to use that, we have this special keyword, this new operator, which when you use new, it doesn't create that variable right there in the local program memory. It actually goes out and allocates it somewhere on this big pool of memory we call the heap. And it stores it there, and you're given back an address to the object. And so that's why this is a node pointer and not a node. So we're going to take the bid, we're going to add to it, and once we've done that, now we get into our fancy logic for appending. And we see an example here. Notice they're actually checking 0. 0 you can kind of get away with because that's null, but that's kind of old-fashioned. I prefer not to use that old logic. I tend to like to be more precise. So remember, this is the append method for our linked list, which means we have access to all our variables in the list, including the head pointer. So we just have a little old if statement. If we say if head equals null pointer, that means if there's nothing there yet, then we do something else. We do something else. So let's talk about this. If the head is empty, if the node has nothing in it, then this, remember, this node is a node pointer. All we need to do is say head equals node. Because remember, this is a pointer to the node that's created out in the heap. The head is itself a pointer to where the start of the list is. So we take that very first node and we assign it to the head pointer. And that's it. And if it's not, then we need to do something else, and I'm going to leave that for just a second. I should probably save all this work, huh? Not that there's ever any problems. I still have an error down there. Symbol size could not be resolved. So this wants to return the current size. Now's a good place to deal with this. So if we go up here, we have an integer. We have a size method that returns an integer. And so what we can do here is in our private variables, if we construct a integer, let's call it size. And here's another trick you can do. You can do equals 0. This is a way to assign a variable and initialize it. I could do it that way. There's one way. I could have done it down in the constructor if I wanted to. So now I've got a local integer called size. And as soon as I created this, notice this method went away, this error, because it was looking for an integer variable called size. So when we're appending, when we add something to the head, or to the list rather, I could just go ahead and increment size. So every time I add a new bid, we construct a node, store it, and we increment the size. And we actually have something that is capable of being compiled. It may not be finished, I may not do all the features yet, but we're getting close. Let's see, what do we got wrong with this? Oh, so I created a new node instance, passing it the bid that we were given in our method. And remember, this is what's called a constructor. When you have the name of the object, whether it's a class or a struct, with parentheses, that's a constructor. So what we could do for this, this is actually a very simple thing. Where's our node? Here we go. So we have a default constructor that does nothing. And let's make another constructor just for our own convenience. Initialize a node with a bid. So we have another constructor definition, only this time we're going to take a bid and let's call it a bid. So when we call the node constructor giving it a bid, all we need to do is set our local bid equal to that struct we were given, a bid, right here. And let's just be safe. I don't want to get fancy and look at ways to override and call other constructors. So let's just say, just to be safe, whenever I create a node with a given bid, I'll save the bid, and I'm going to make sure that next pointer is null, because at the moment this is just a node. We don't know what it's pointing to. The node doesn't know where it points. The node is just a little data structure that is used to represent an item in the list. And that's an important concept. Your node should not be doing any kind of manipulation of its pointer. So it's okay to initialize it, because you want to, every object, every class, every struct should be responsible for maintaining its own state. But the business logic of what the next pointer, the next node pointer points to, is not the responsibility of the node. It's actually managed by the list. So this is just a generic structure that represents a node instance with no logic. Once I define this constructor, and I go ahead and save it and compile it, this should go away. So now I'm able to create a new instance of a node, giving it a bid. So again, I just want to quickly go back and follow this logic through. In the main method, we're going to, when we choose load, we're going to call load bids, which load bids is using the for loop over the CSV file. For every row in the CSV file, we're going to create a bid, initialize the variables, and then we're going to call the append method, giving the append method the bid that we just created. And the append method is, the append method is going to take this bid and create a new node instance with that bid, and then point to it. Now, what happens if the head pointer is not null? So this is if it's null pointer, else if it's not, then with the linked list, we need to go to the end to find it. Now I'm going to jump ahead and show you a little optimization. One of the things I remember some of the discussions are, and that's why this list, notice they have a tail pointer. This is it's not a cheat. It's still a singly linked list, because each of the nodes only has one pointer to the next node. But there's no harm in making your list be more useful and optimized. So if we also had another pointer, not only to the head of the list, but if we created another node pointer called tail, with the intention that it would point to the tail of the list, and I'm going to show you a really cheesy, difficult C++ optimization. You could do this: head equals tail equals null pointer. This is I'm putting this here because you're gonna run across code someday in C++ that does this. It's a very common trick. This is equivalent to 2 separate lines. It's just that C++ people seem to really like to be full of shortcuts and cheats and little tricks. That's the same thing as what we have here. You could have multiple statements that are all initializing each of the variables to null or you could do something like this, head and tail equals null. So now the idea is that the tail pointer is going to point to the last one in the list. So if the head is null, that means there's no nodes. So we're going to set the head to point to the node, and we also need to set the tail to point to the node because there's only that one entry. So both head and tail point to this one node that we have at the first time a first node is added to the list or appended. Now, if the list is not, if the head is not null, that means we have something. So we have at least one node in there. So now we just need to operate on the tail portion. So we have to account for two cases. The tail could be null, or the tail could be a value. And what we do is we first need to test that. We say if tail is not null, that means if the tail is pointing somewhere, we are it. And I'll show you visually in a second. This is the condition we're trying to account for. If the tail points somewhere and we're going to append, we have some new node that we've created that we haven't attached to the list. What we need to do is a couple of things. We need to get this last node's next pointer, this last node where the next pointer is null, that needs to now point to the new node. And then we want to make the tail point to the new node. So we have to do really two things here. So we start by saying if the tail is not null, if the list has a tail somewhere, then we want to take that tail and we're going to use the dereference, which is the dash arrow. And notice as soon as I type it, you can see it. We could say tail. I'm pointing to the last node in there. I want to take its next node. This is the next node of the last one in the list, right? So what happens is I want to reach over to the tail, the last node. I want to take its next pointer and point to this new node that we're adding. So now the chain is complete. So the last one that's there has to point to the new one, and then we take that tail and we point to that new entry as well. So we say tail.next equals node, and because node is a pointer, so we just simply set it to be that new one. So now the next pointer of the last node points to the new one. And then, actually I did this here, I didn't need to. What I should have done was this would have been more optimized. In this case, we could say tail equals node, because whenever you add a node, and I did it this way, oops, I always do that. So let's walk through this logic. I've got a new bid. I create a new node somewhere in memory using that bid, and now I've got a pointer to it. If the head of the list is empty, then we simply make it point to this new node. Else, that means the head is not empty, so now I need to go to the end somewhere. So then we check the tail. If it's not null, if the tail points somewhere, we go to that node's next. We go to that node that's pointed to by the tail. We take its next and point to the new node. Regardless of whatever we're doing, whether we set the head or we find the end and point to it from there, this new node that was appended to the end is always now the last node. So now we set the tail of the linked list to be node. And if we did this correctly, we might actually be able to do something. Let's just take a chance. First off, if I go to my local workspace, you notice there's a debug folder, and you notice we have a executable file. I'm just going to be lazy and take these two guys. Oops. And copy them down here so I don't have to do anything special. I'm going to copy this address, open up a command prompt. I'm going to change to this address. And you can see there's our executable file and there's our two things. So let's do lab 3. And I won't specify anything else for now. And sure enough, we have something. Let's see what happens if we can just keep appending. Look at that. 179 bids read. It took, this is actually wrong. It's not milliseconds. It's clock ticks, I think. But anyways, it took a extremely tiny amount of time to do. Just to show you the difference and the importance of these things, let me copy this file name. See, first if I have to exit, I want to start it again, but I'm going to pass the name of the new file. Oops. And if I did this right and it works and doesn't crash, ooh, did you see it hang for a second? So instead of 179 bids, we read almost 18,000 bids. And what took 3/100ths of a second to read 180, it's now taking a half a second to read 18,000. Now we haven't implemented the display all. We'll do that next, or the find. So at this point, I'm going to pause to see or ask if there are any questions. I've been kind of rattling on for a while. No questions?
Nope.
All right. Make sure I exit out. And we're going to take a look at the next step, which is, I'm going to skip the prepend for a second. I want to jump right into the print before we get fancier. So in order to print this, let's go back to our main method here. So remember, we have a local instance of our linked list class called bidList. And when we get to the load routine, we load the bids, giving it the address of this bid list. So at the end of the day, and you can see it because that bid list, notice how we're able to call the size method, because every time we added a node, we incremented the size. So we're able to call the size method on it. And we're using the same bid list variable, so we know that we have data in here. And so when the menu option is 3 for print, we simply use that same bid list. Remember, it's a linked list instance. It's a class of type linked list. So on that bid list, just like we called the append method here, just like we call the size here, we're now going to call print list. So given our list, what do we need to do to print it? Let's see here, linked list. In order to print, let's see if they have one here. They show it perhaps. Prepend we'll come back to. Insert list traversal. If you want to traverse the list, a linked list, you start by getting the head pointer. You set your pointer to the current, you basically have a node pointer which points to the current node that you're working on. You initialize it to the head or the start of the list, and then you can keep changing current to next, next, next. So printing and using a linked list is actually really very easy. We start by making a node pointer, and we'll call it current. And we'll set it initially to the head pointer of the list. And then through the magic of multiple screens because I don't feel like typing all this. I'll probably get it wrong. We have a little while loop, and we're just to be safe, we're going to say while current is not null. Now, why would we do that? It's possible that the user running this, for example, didn't load the list first. If they started it and then immediately went to print, our initialization would have had the head and the tail be null. So there's a condition that could arise that we don't have any entries in there. If we just started referencing this data, we would get a crash because we would be attempting to access memory that is not initialized. So we have a while loop that says while current is not null. Oops, I forgot a line here. While current is not null, we're going to send to the output, to the console out, the current. Remember, current's just a pointer, like anything else. We're going to go to the bid that's pointed to here and print out the ID, a colon, the title, looks like a bar, the amounts, and so on and so forth. And then we set the current pointer, right, which initially is the head. We're going to set that to be this. It's this node. So the first time through, current is going to point to here. We're going to print this bit, and then we're going to say the new current pointer is whatever is in next. So then we change the current pointer to be here. Now it's going to point to the second one. We print that bid, and then we set the current pointer to be next, which is the third one. And we're going to basically just keep going through there, looping through the entire array. It's a very simple. If you eliminate this, that single little loop with one statement inside right there will walk through the nodes. It's that simple. You just initialize it to the head and loop through, and for each node you set it to the next, and then the next, and then the next, and then the next, until you've gone through the entire list. I'll put that back. We'll save this. We'll file it. And let's go back here. Only I'm not going to use the big file because it takes a lot longer. I think last time I was playing around doing this, it took, was it 40 seconds? So I'm just going to leave it to the defaults, which is the smaller file for just December. Call load bids. Notice it took, oh gosh, it's even faster. This thing must be getting warmed up. It's kind of like my car. Now that I've loaded them, I'm going to call the display function or method. And there they are. So we just zipped through 179 entries in the node in the list, and for every one of them, we set initially we set it to head. We printed out the bid that's pointed to by current, and then we change current to point to the next one, and print that one, and so on and so forth. It's that simple and that fast to zip through a set of nodes in a list. So let's see, prepend. That one might seem like it's a little trickier, but it's actually not. Much like we had to do with the, let's see, do I have the append here? Good. Let's see if I can, I'll hide this. So with append, we went to the head, put the node there, or else we went to the end and added it onto the end and made the tail point to that new one that's now the end. With a prepend, we do it very similarly, only we do it to the start. So there's a insert gets a little tricky, and I didn't want us to have to do that because I didn't think it was really that interesting. That starts to get just tedious for no necessarily good reason. So I chose to go with prepend. So with prepend, in order to prepend a new node at the front, what we have to do is we want to basically stick a node in front of here. Now head points to here. What we want to do is make our new node point to here, and then make the head point to the new node. So it's really just shuffling pointers around, and we've changed the list. So the logic for that is we're going to say if head is not a null pointer because we want to make sure we're careful. Remember, even though we're saying it backwards, what that really saying is if there is something pointed to at the head, then our, oops, I almost forgot this. Focused on the logic so much. So got to remember to create a node from our bid that was passed in. So if the head is not null, then this guy is going to get inserted. So this guy's next pointer has to point to what was already in head. So that's really a very simple operation. We'd say node, which is our new one, next. So we want this new node to point to whatever the head is pointing to now. And then just like we did before, we're going to say head equals node. Just like we did with the tail, it's always going to be there. And because we inserted one at the front, we still want to increment the size of the list. I don't remember what we had for prepend. What does prepend do? Let's go look, see. Prepend is that even called? Display, find, remove. Well, you know what? Let's add a 6, just for grins. This is going off-road, trying something live in a demo. If we're going to prepend a bid, we need to, I'm going to cheat here. So here we have a bid, we have a method already, it's called get bid. So if we say enter, then we're going to store this. This doesn't append, so this is actually not that really dangerous of an operation. What do we say it was, number 6? So I go down to number 6. And then drop this in, only instead of calling prepend, or excuse me, append, we're going to call prepend. And this will be interesting because when I display it, yeah, we can make this work. Recompile it. Let's just run it with a simple one. So first we'll load bids. Good, they're all loaded. Actually, the enter was going to do an append, so that's all right. We'll do a 1. No, a 6. So we'll give it an ID of 1, 2, 3, 4, 5. Title, COCE, CS-260 is awesome. The fund, we're going to pay for this out of our checking account. And we'll lessen amount of this. Can't be that expensive. It must be what, $9.99? It's not that good of a course. Now, we displayed it. So there's what the bid looks like. But we also had it prepend it. So if everything worked right, I now should be able to display all bids and see that new bid. And it better be in the front, or else I'm going to blame Microsoft Windows. Oh, there it is, right in the front. Make sure we exit. And there's a prepend. So now we get to something that's probably bugging everyone. The remove logic. How do you handle removing stuff? You give it a bid ID. The signature for the remove takes a bid ID, so we need to have an ID to remove. Actually, before I go into remove, let's go to search, because that list, that logic is going to be what we reused. And you can actually cheat a little because we already have code that walks through the list. We're going to borrow that in just a minute. Let's hide the remove so that's not in the way. And the search is going to take a bid ID. So as always, we're going to have a node pointer. Actually, why don't I just copy this because I show you what you can do with this. I'm going to copy this logic, and the reason I'm copying it is because a lot of the code is the same, right? We're going to start by pointing to the head of the list. While it's not empty, we're going to keep spinning through. Only, and remember that the node is going to return, excuse me, the search is going to return a bid instance. So here's where we got to make our changes. So we're going to say, if current bid dot that's right. Why are we not getting? Current is a no pointer. Current bid dot, there we go, bid ID. So I'm going to look at the bid ID of the bid at that current node instance, and we're going to use this is a string method called compare, which, by the way, if you just type the dot, you'd actually see all the methods, and we're looking for one called compare. And it takes, what we're going to compare that to is the bid ID that we copied in, and the compare operation will return 0. This is a good time to take a little side trip. If we do, I think it's what, CPP ref, reference.com. There's a website called cppreference.com, which is a C++ reference, and it has everything about C++ or C that you might want. We're going to go to the string library. We'll start with a basic string. That's what we're using. And if we look at it, you can see all the members and the member functions. And the one that we found or we're going to use is called compare. So from here, we can take a look and see that all the various signatures, and then there's some notes. Reason I was choosing one, if the, let's see, if data, so compare takes two arguments, depending, well, so with comparing, you're comparing two things. If the data matches the argument you're checking, and the compare operation returns if the thing that you're checking is less than the argument, then it returns a value of less than 0. If the two match exactly, it returns an equals, and if the argument, excuse me, if the thing that you're comparing is larger than the argument, then it returns a greater than 1. What it's returning is actually the position where they differ. So for our purposes, we're going to say current node, that bid, its ID. We're going to call the compare method because this is a string, so we're able to call the method on the string, and we're going to compare it to the bid ID that we were passed in. If the two are equal, then we know we found the node that has the bid that we're searching for. And if that's the case, we just have a very simple little return current bid. And that's all it takes. So when we're searching, we initialize the current pointer to the head, and then we go into a loop while it's not null. If that current pointer's bid ID equals the one we're searching for, then we return that bid. Otherwise, we make the current point to the next node, loop around, and we very quickly spin through. So let's just see if this works. Save it. We'll compile it. and we will run it, load the bids, 179. Then we're going to call find. And as soon as I call find, it went and returned. Remember that 981.109? The main method has a default. If you don't pass any arguments, it's going to default to this file and this bid key. So I could cheat a little. Let's copy this. I'm going to exit. I'm going to run this, and I'm going to pass that file name in. Let's go find that list of bids. Let's find something interesting. Oh, there's our bid IDs. Oh, what's really good? Samsung TV, washer dryer. Oh, let's look for a school bus. That sounds interesting. 98260. I'm going to copy this value. And oops, I want to paste in 98260. So now the program is started. We load everything up again. And then this time when we call for, we should come up with 98260, a school bus. And there it is. Now we could have enhanced this by making the find prompt for a string and then, without having to exit and reload, but that wasn't really key to what we're trying to do here. It was more about being able to search a linked list, and you do so with the walking through the nodes using this current pointer. And so if we're going to remove, running a little bit low on time, if we're going to remove a specific bid, I can't copy this code, but I can reuse this code. I can't call it. So now that I already know how to search for a node, we can basically paste this in because we're going to be given a bid ID, and we're going to say, start at the head. Once we find it, now this is where it gets a little trickier. So, excuse me, if we go back to here, let's say we were searching for this one. So we'll initialize it at the head. We'll get to this point. If we want to remove this node, then what we need to do is basically have this node not point here, but point there. Now we already have that because the node that we found, we need to take it and make it point to the previous one. And so this is where it gets a little tricky because you have to actually look a little further ahead, because in order to change this one, I don't want to be here at this node because I don't have a way to go backwards because it's not a doubly linked list, it's a singly linked list, so I can't go backwards. So what I actually need to do is what we call look ahead. So we start with a current node. Actually, let's think about this a second. We have current. So I really need to look ahead too. Think about this. Let's do this one first. There's actually a special case. Oops, sorry, do it again. There's a special case we have to handle, and that is the head pointer, because you can't go jumping ahead. If there's one node in the list and that node is matching, then we need to make the head go away. So we'd say if, and I guess I could be careful. So we say if head is not equal to null pointer. So we want to make sure we don't make mistakes and cause it to crash. Then we say, oops. Now we can say if the head's bid equals what we want. So we say if head bid, come on, bid ID compare to the bid ID that we were given. So if the head pointer, the head node is the one that actually matches, and since it's going to be removed, if the head is the one that matches, removing it is simply a matter of doing this. We say head equals null pointer by setting it to null. Oops, actually I forgot to do a delete. Let's do it this way. Yeah, so we'll say delete head, and then we'll initialize it to null pointer again. The delete operation, because we were using, if you remember, these nodes were created originally by using the new operation, whether it's append or prepend, we're using new to create a node out on the heap. You need to free that memory up, and the way they do that in C++ is with the delete method. So that head pointer now needs to be freed up. So we call delete, and you're really giving it the pointer of the information to be deleted, and then we want to make sure we initialize the head to null. And just to be safe, if we take the head away, there is no tail because everything is gone. So we want to be very careful about cleanup and set the tail to null. So this is a special case when I only have one, when the head matches, and I'm just going to erase it. So if the head doesn't match, then we're going to set current equal to head. But now we already know the head doesn't match. What we have to do is actually look beyond the current. Say next. So that's the node after that. We want to see if its value, so that we're actually jumping ahead too. And I'm just going to copy this. Bid. I'll walk you through this in a second. Oops. Did this in the wrong place. Sorry about this. Getting ahead of myself. Up there, and then take this off. I meant to do it on the if. So, oops, where did I go here? Talk you through this again. We already checked the head. If the head points to something and it matches, we delete that. If it doesn't match, we set current equal to head, which we know already doesn't match. Remember what I said? We have to keep looking ahead. So we want to look at the next. So if the current is head, then it's going to point to here. We're going to look at the next one and see if that one matches, because if that one matches, the one in front of it, then we need to change this next to point beyond it, basically eliminating this. That's what we're trying to accomplish here. So we do this by saying if the next pointer is not null, it's not at the end of the list, then we check that next pointed to node's bid. If that matches, then we have to do some fancy footwork here. So the first thing you want to do is create a temporary pointer, because we gotta remove this guy from the list. We'd have to remove this one from the list. What we're going to do is we're going to point to that one. So we're going to call it, let's say, temp node. Actually, we're going to initialize it to be current next. So we're here at this one. We're looking at the next one. If that is the one that matches, we want to create a temporary pointer to it to hang on to it. Then we're going to fix up these guys to point to it. So we're basically removing this from the list. And then once it's been removed from the list, we can then delete it. So this points to the current. Oh, gosh. Now, we want to make our current node, make current node point beyond the next one. So we'd say current next, which right now, oops, current next is pointing to this guy. So we're going to make this point beyond. And the way you do that is we're going to say the current next is going to equal the temp nodes, because that's the one we just saved, next. So what we've done there is we've taken this next pointer, we've taken this next pointer, that's the temp one, we've taken that next pointer and we've copied it to here. So now this guy points here, and this guy is no longer in the list, in the chain of stuff. Once we've done that, now delete that temp node. So we'd say delete temp, voila. So we look beyond the current one to the next one. If that guy's bid matches, then we grab a pointer to that next one, and we make the current one point beyond, which is what the next one was pointing to. We're going to skip ahead one, and that's going to free up this temp node in the middle, and we can then delete it. And of course, because we remove something, we want to decrement our size. And at that point, we're done. We've removed what we wanted to. We need that turn. And so that's what a remove does. And if I did all this well enough, it should compile. So we're using that same bid key. So let's see if we can make this happen. If we run this and we load it up, 179 bids, I'm going to call remove once. Nothing happened. And if I just do a display, can I do a display? Does display show display all bids? Doesn't show you a count. But remember, what did we say it was 98109 if I remember correctly? Go to Eclipse. The default was 98109. Fortunately, these are in sorted order. And sure enough, there's no, oh, no, they're not in sorted order. So we'd have to do something really ugly like this. I wonder if I can make this work. I want to copy. I don't know if I copied it or not, but we'll try. Oh, didn't do that. Oh, no. Good. We copied them. Notice it's 178 entries, not 179. And just to prove the point, I'll do a find for 98109. Not found. So there, we've done a remove. Make sure I exit out of here. Come back around. So we did our search, we did a remove, print, append. So I think we've covered everything. Okay, now it's time for questions.
How much time do we have?
As much as you want.
Okay.
So I get tired and fall asleep.
Okay. On the remove method.
Yep.
There's only people in the class.
There's
Where is it? If the head node matches, you set the tail pointer to null. What if there were other nodes? Is that correct?
You're right. I shouldn't have done that.
Okay. Okay, I was concerned. All
yeah,
right.
I was thinking about initializing, and I thought, well, you can initialize one, initialize them both. But you're right. Good catch.
You would switch the head to the next one, right?
Well, tail is still going to point to the tail. If the very first one is the one that matches, we delete it, and then we have the head.
Yeah, so
actually, you're right.
Yeah, if there's a node 2, you'd set head to that
we
one.
need this. Yeah, we need to do this too.
Okay.
Oh, no. We got to make this right.
I went back and forth on this so many times.
That's what happens when you're kind of winging it a little bit. So if the head one matches, there may or may not be one afterwards. So what we want to do is,
Yeah.
actually this will work.
So,
So we'd say head next. So if the head pointer matches, then we're going to create a temporary node for the next one. And then we'll delete the head.
yeah.
And then all we've got to do is say head equals temp. Right?
Yeah, well, at 153, you still got head equals null, so you might want to kill that.
Let's get rid of that.
There you go. Okay.
So the logic is if the very first entry in the list is the one that matches, we want to basically grab this next node so we can hang onto this pointer, make the remove the head, and then have remove that node right there, and then have the head point to the one beyond. So let's see if we did this correctly. So if the head matches, then we're going to point to what's beyond it, and then we'll delete it, and then we'll make the head be that new one that was pointed to beyond. And this works in both cases. If head was the only one, then its next pointer would be null, which is okay, and then head would get set to null. If it actually points to something, we simply delete it and then make the head pointer be whatever was beyond. Do you agree?
Yeah. Yep.
Okay. Any other questions?
The compare operation. I think I just did equals comparisons. Is compare generally safer?
It is, because when you're dealing with objects and object instances, the reason it gets a little advanced and object oriented, but what happens is the reason you have a compare method is so that you, the person creating that class, can implement logic that makes a comparison meaningful to you.
Sure. Okay.
When you do the equals, if you think about it, right, this is a string. This is a string, right? But we didn't really talk about this, but the string is actually a class instance that's created in memory as well. So what you're really doing is comparing the two strings. When you say equals, you're saying, is the address of string A equal to the address of string B? So if they're truly 100% pointing to the same identical piece of memory, the same string value, that works. But if you had another copy of a string, call it string copy, okay, they would not match, but technically those strings may have equal values, and that's why you have a compare method. Does that make sense?
It does. It does. I think I just stuck with equals because they're all integer values in this well.
Yeah,
I'm assuming they're integer values for pointer addresses. Is that correct?
Right.
Okay.
But they may not point to the same thing,
Right.
although the values could be equal, or they could be equivalent, I should say.
Yeah. Okay. And of course, you're right. You could just override compare if you had a special object you want to do a different type of comparison. Okay, that makes sense. I don't have any other questions.
All right. No other questions? So I think we were successful. Any questions on this week's? Any tips or pointers I could give? We haven't had a chance yet to dig into that. So what I will say is that this week's exercise is what appears to be subtle at first, because when we talk about stacks and queues, they're really, so now that we've got the basic ability to manipulate a linked list, stacks and queues are very simple. Queue you always append to the end, so all you really have is an append method. With a stack, you put things on the front, so you have a prepend method. So you've actually built stacks and queues, you just didn't know it. We didn't call them that. But when you get into sorts, the selection sort's not too bad, although you'll find it's to be quite slow. got here? The selection sort runs fairly quickly because you're just comparing and swapping, and you're going to loop through until there's no more sorting to be done. But when you get to the quick sort, come on. When you get to the quick sort, you have this partition algorithm that you need to support. So quick sort works off of partitioning at some point, midpoint, and you keep breaking the partition down smaller and smaller until you get it done. In order to do that, so here, notice there's a partition method. You're going to need to implement that. And then the actual sort routine is going to compare, which I think is right there. So here's your partition. Now you could probably get away with trying to copy this in, but it's not exactly the same. You're going to have to modify it to support bids. And I think we said we're going to sort on, I forgot what we said we were sorting on. Give you a quick peek here. We're supposed to sort on the title. And then when you run this, you're going to be able to see the results of sorting with selection and versus sorting with a quick sort. And you should see quite a bit of difference if they're implemented correctly. So that concludes this lesson, and we'll plan on doing this again next week. And I will post this onto the Blackboard for the school, or for the class rather. So thank you all, and enjoy the rest of your evening.
Thank you.